Sample problem 16.17. Determine the Kb of the acetate ion, CH3COO negative, Ka of the methyl ammonium ion, CH3NH3 plus, Kb of the fluoride ion, F minus, and the Ka of the ammonium ion, NH4 plus. So this is the issue of conjugate acids and conjugate bases. So remember, the idea is this. If you have an acid, which we'll represent as HA, an acid can be thought of as something that reacts with water and donates the H plus to the water to give us the conjugate base and the hydronium ion, which is the conjugate acid of water. Okay? So acids form conjugate bases. Likewise, if we take a base and react it with water, so this is a base, we can think of a base as something that accepts an H plus from the water molecule to give us Hb plus. And it will also form the hydroxide ion. So this is the conjugate acid of B, and then this is the conjugate base of water. Okay? So the key to this one is you're going to need access to two tables. The first table is table 16.16. And I'm sorry, I think it's table 16.6, not 16, sorry. There's not that many tables in this chapter. Table 16.6 and then table 16.7. Those are the two tables you need, so you can look these values up. So here's how we're going to approach this. In part A, we want to find the Kb of the acetate ion. Okay. We're looking for the Kb, but if you take a look, it's not going to be in either of those tables. So here's what we do. We use the following relationship, a very powerful one. The Ka for an acid times the Kb for its conjugate base is equal to Kw, which is 1.0 times 10 to the minus 14. Of course, you know that's at 25 degrees C. So in other words, if you look up the Ka for this one, and you want to know what the Kb for this one is, you use the following relationship. Ka times Kb equals Kw, or Kb equals Kw over Ka. So we can find the Kb of a conjugate base, even if we don't have it in a table, if we can look up the Ka for the acid that formed that conjugate base. Likewise, we can do the same thing here. If we can look up this Kb here, we can find this Ka here using the same logic. Ka is Kw over Kb. And that works because we know what Kw is. That's a constant. Okay, so let's try it for part A. We want to find the Kb for acetate. This is acetate. It's not in table 16.7. So what do? We look up the Ka for acetic acid. So if we're talking about CH3COO minus being acetate, the conjugate acid is CH3COOH. And that's acetic acid. And the Ka is 1.8 times 10 to the minus 5. So that means the Kb for acetate is Kw over 1.8 times 10 to the minus 5. So that's 1.0 times 10 to the negative 14 over 1.8 times 10 to the minus 5. Okay? that easy. So we come over here. 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, and we get 5.6 times 10 to the negative 10. There's our answer for part A. Let's try part B. For part B, they want you to find the Ka of the methyl ammonium ion. So we want to find Ka. And the methyl ammonium ion is CH3 NH3+. Well, guess what? You're not going to find it in table 16.6, right? 16.6 is the Ka values. 16.7 is the Kb values. It's not in there. So what do? We say, okay, take off the H+, and that gives us the base. This is the base form. This is the acid form. With the H+ is the acid. Without the H+ is the base. So we see if we can look this up anywhere. So we go to table 16.7, and in fact, methylamine is there. Kb is 4.4 times 10 to the minus 4. Okay, which means that Ka is Kw, 1.0 times 10 to the minus 14, over Kb, 4.4 times 10 to the negative 4. .27. Let's round it to 2.3 times 10 to the minus 11. So there's our Ka value for the methyl ammonium ion. Okay? Well, that's B. Let's try part C now. I'll make a little room here. So part C, they're telling us we want to find the Kb for the fluoride ion. Well, that means if we can't find the fluoride ion in the Kb, so it's not in table 16.7, that means we go to table 16.6 and we look up the Ka value for what would be the conjugate acid. You just add an H+ to it. So H+ and F- gives you HF, hydrofluoric acid. So we go to table 16.6 and look up HF, and it's there, 7.1 times 10 to the minus 4. Okay, so Kb, would be Kw over this Ka. Okay. So 1.0 times 10 to the minus 14 divided by 7.1 times 10 to the minus 4. 1.4 times 10 to the minus 11. And there's our answer for part C. Part D. Part D, we're looking at, we want to find the Ka for the ammonium ion. That means we want to look up the Kb for, take the H+ off. Remember, the acid has an extra H+, the base has one fewer H+. So we're going to look up the Kb for NH3. Well, that's easy. We did that in a previous problem. But that's in table 16.7. So that means Ka here would be Kw over Kb. And you actually get the same answer we got for part A, I think, because we did the acetate ion. 5.6 times 10 to the minus 10, because the numbers are the same. Okay, so notice one thing. I'm going to come over here. Ka is kW over kb. The larger this is, the smaller that's going to be, right? Or another way of thinking about it, that product is equal to 10 to the minus 14. So if this one's bigger, this one's going to be smaller because the two of them multiplied together have to equal this number here. So the stronger the acid is, the weaker the conjugate base is going to be, smaller the Kb. The stronger the base is, the larger the Kb, the weaker the conjugate acid is going to be, which is smaller Ka.